So welcome back. We are now into our next lecture, next part of this real life reactor. So recall all from first part of this lecture, first part of in this first lecture in this part. Uh, we had looked at plug flow reactors, trying to look at temperature rise across the tube, temperature rise between inlet to outlet. Then last lecture we devoted exclusively to well mixed continuous reactors, adiabatic, diabatic, transient means dynamic behavior, and multiple steady states. Right? This lecture we are going to devote exclusively to batch reactors. You might think that batch reactors are so easy. Now you will see all the complications that happen and all the considerations that we have to make because of exothermicity of the reaction and how things change based on now, because heat is generated, heat is removed, how the behavior of the reactor changes very dramatically. So this is where we are in our course. We are in part 2 of our course of real life reactors. Couple of things I would like you to revise before we go forward. What is the physical significance of the term UA by V rho Cp? We talked about it in the last class. If you don't remember or if you are not able to understand, go back and see the lecture. For a CSTR, now I am writing CSTR, but as per our classification, what we should actually write is well mixed, continuous, steady state reactor. Write an expression for rate of heat generation. Next question, what is the cause of multiplicity of steady states in well mixed reactors? We should not be writing CSTR now. I have written it just so that you are comfortable, but we should be writing well mixed, steady state, continuous reactors. What is meant by extinguished steady state and ignited steady state? What determines whether the steady state is stable or not? These are all questions that we discussed in the last class. Just quickly revise that so that you are in a better position to understand what is going to come in this lecture. Now we are going to see exclusively in this lecture on batch reactors. So first of all, exothermic reactions in a batch reactor. So imagine that the batch reactor has been filled with reactant and the reaction starts. So at T equal to 0, we have filled in the reactor with T equal to 0. So at T equal to 0, inlet initial concentration is 2 kilomoles per meter cube. Initial temperature is 298 Kelvin. So now I is denoting initial, not inlet, because there is no inlet. It's a batch reactor. Okay, you can use all these physical properties. Calculate the profile of temperature and conversion as a function of time. So write unsteady state equations for material balance and for energy balance, and I want you to see the sensitivity of parameters delta H and E and UA by V or UA by V rho Cp if you like. Pause the video, write these equations for yourself, solve them for yourself, and then only go forward. Okay, here is what you will write. Material balance, if you write accumulation in minus out minus reactor. Now there is no entry, there is no inlet, there is no outlet, so that is 0 and outlet. So minus V dCA by dt is K naught e raised to minus E by RT Ca and V. Simplify that. We write in terms of XA. So dXA by dt is equal to K naught exponent of minus E by RT into 1 minus XA. And at T equal to 0, Ca is Ca initial, which means XA is 0. Enthalpy balance, write that in an unsteady manner. Same way, write that, pause video, write it for yourself, then only go forward. Here is what you will get. Accumulation, no entry, no out, in out, both are 0. No flow coming in, no enthalpy coming in, no flow going out, no enthalpy going out. Heat generated by way of reactions, first order reaction in this particular case. Heat removed by jacket. Again, take limit as delta T tending to 0 and it becomes a differential equation. So dt by dt K naught e raised to minus E by RT Ca V minus delta H and heat removed, generation and removed. So again we can write in terms of theta, you will get this expression d theta by dt is k naught e raised to minus e by rt 1 minus xa ua by v rho cp theta plus alpha. Alpha is like how heat is being removed, Ti minus Tc. So if your initial temperature and the coolant temperature is the same, alpha is just 0. At t equal to 0, T is Ti, which means theta is 0. Right? So do this for yourself. Do this for yourself. Make sure that you get this expression. So now I have two equations, one material balance equation and one enthalpy balance equation. I need to solve these two equations, differential equation. They are coupled. Theta appears in first equation, xa appears in the second equation. They are coupled. They have to be solved simultaneously. One way is to solve using MATLAB, something like that, or you can use Euler's method, or you can use Runge-Gupta or other methods. Okay. There are two time scales now. Remember, one is a reaction time scale K, and one is this heat removal time scale. Recall, this is our K, K naught e raised to minus e by RT. This is our reaction time scale or reaction rate K, and one is this UA by V rho Cp or MCP. This is our heat removal time scale. So, or 1 by K is a reaction time scale, and V rho Cp by UA, that is our heat removal time scale, time constant for heat removal. So interplay of these two will give rise to different behavior now. So plot this data, plot it for different cases. It is minute inverse, not minute minus 1, minute inverse. Let me just make that correction. Let me make that correction. Minute inverse. Minute inverse. Okay. What I want you to do is plot how theta changes with time and how xa changes with time. Plot this for yourself. Solve it for yourself. Then only go forward. Pause the video. What I am going to show you is this solution in a spreadsheet. Let's say Excel here. I put all these equations I have solved with respect to time. What I have plotted is xa or theta versus time. So red tells you the temperature, it's a dimensionless temperature theta, and this blue tells you the time. Blue tells you the conversion. Look at this. This I will just remove a little here. But this is for one. Sorry, this is for one particular case. Now what we'll do is we'll change the value of E by R, and we'll see how this changes, or we'll change the value of delta H and see how this changes, and we'll change the value of UA by V and see how this changes. So if I reduce UA by V, means I am reducing the heat removal. So now temperature will go to higher value. See, peak value of temperature, as we increase time, temperature goes up because now heat generation is more than heat removal. But then as temperature goes up, then heat removal picks up, and then heat removal becomes more and more and temperature falls. So this peak temperature I get after 200 minutes, and the peak temperature is 0.2, and the delta T max is 41, means temperature is rising by 20 degrees centigrade. If I reduce it further, UA by V, You see peak temperature is increasing now, 0.5 means it is increasing to by 20 degrees centigrade. Further, you see peak temperature is very high. Temperature rises by 40 degrees centigrade from inlet within just 150 minutes. Okay, both these curves overlap with each other. So, like a laboratory reactor, if I operate a laboratory reactor, which means a high UA by V, high surface area in a laboratory reactor because size is small, I see very small rise in temperature. Maybe it rises only by 4 or 5 degrees. 0.05 is the dimensionless rise in temperature. 0.05 times 40, 2 degrees centigrade. That's all the rises. As I go to a plant scale reactor, my heat transfer area reduces, A by V reduces. The peak temperature goes up. Peak temperature here is 20% or 30% of 41, which means about 10 degrees. Here it is about 50% of 0.5 of 41, 20 degrees centigrade. So now you see in this part, that's where we have to be careful. Temperature is rising with respect to time. We could have a solvent that is vaporizing. We could have a side reactions that take over. We could have decomposition reactions, which are even more exothermic, and then it could lead to runaway condition. So predicting the temperature rise with respect to time is very critical. Predicting the peak temperature is very critical. If you change E by R, make the reaction less sensitive to temperature or make the reaction more sensitive to temperature. If I make it less and less sensitive to temperature, the peak is smaller and smaller. If I increase E by R, reaction is becoming more. Now you see this behavior. At 120, 130 minutes, temperature is maximum and it reduces. You see the peak temperature is 80% of 41. 80% of 41 means it is about 30 degrees centigrade. Increase it little further. See, 90% of 41, 37, 38 degrees centigrade. You see how sharply this increase is. You see how sharp this increase is. You see how sharp this increase is. Within a span of maybe 10 minutes, temperature is rising dramatically by 20-30 degrees. And this is what causes our uh, runaway kind of conditions. You see, initial increase is gradual, but then it picks up very quickly because energy of activation is high. It responds to, or it increases with temperature very dramatically, and then as if reaction picks up, and then you get a big exotherm. Peak temperature is very high, and it is at this predicting this peak and the value of that peak is very critical because our product may be sensitive, heat sensitive. It may start decomposing. It may reach auto ignition temperature of the solvent. Whole reactor just catches, explodes, fire, right? Safety consideration, these are very, very important. Okay, now let's remove all this. Let's or I will change them dynamically. So delta H is now minus 20 kilocalories per gram mole. Let's reduce delta H, right? So delta H is now, well, let's okay. So delta H is now minus 10 kilocalories per gram mole. UA by V is, I will change the UA by V. UA by V is 5 here. I will change it to 15. Yeah, 15. So delta H is minus 10. UA by V is 15. And the dimensionless temperature rise, delta T max is 20.8. 20.8. So if reaction is has little exothermicity, we don't have to worry. Our peak temperature is only 10% of 20, means just by 2 degrees. Now we'll see what happens as I increase delta H. So minus 10,000, let us increase it to minus 20,000. 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 . 20 So minus 20,000 kilocalories per kilomole or minus 20 kilocalories per gram mole. UA by V is 15 here. Peak temperature rise now is 41.7. That's what our 41.7. So peak temperature now is 50%, 60% of 41.7 means peak temperature it is increasing by 20 degrees centigrade. And it's not just what is the peak temperature, how fast it is rising, because that's the time available for us to respond. That's the time. Within these 10 minutes, everything is happening. Increase it little further, make it minus 25 kilocalories per gram mole. You see, minus 25 kilocalories per gram. Peak temperature is now delta T max is 52. 52.1. Peak temperature is 80%, 0.8, 0.9 times this 52 means by 40 degrees centigrade it is rising. And it's not just that 40 degrees centigrade, it is, you see how fast it is rising. It is rising in a matter of few minutes to a value 50 degrees higher than inlet temperature. That's the time window that I have. That's where all these runaway kind of scenarios happen. You must have heard of so many accidents that happen, right? Increase it little further. Right, so just blown up. Or I can increase my UA by V now. And reduce this, increase this. So now it is 30 kilocalories per gram mole. Delta T max is 62.5 degrees. Peak temperature rise is 70%, which means it is 42 degrees centigrade. But you see this peak, how sharply it is increasing. Within a couple of minutes, it has increased by 40-50 degrees centigrade. That is what we have to be careful about. That is what causes runaway kind of conditions. All these are coming from here, heat generation and heat removal rate. This is what I was talking about, effect of delta H. As I increase delta H, 10 kilocalories per gram mole, 20, 35, 45. You see how the peak temperature, delta T max is increasing and the peak temperature is increasing. So here, if you see minus 45 kilocalories per gram mole, delta T max is 93 and it is 80% of 0.8 times this temperature rise. That means it is increasing by 70 degrees centigrade. And that increase is actually happening in this duration. So from here to here, this is just a 5-minute or a 10-minute window. This is what leads to our runaway behavior, because at this high temperature, some other reactions can happen, solvents can degrade, decomposition, some auto ignition temperature may be reached, suddenly it goes up and then you have all kinds of problems, you have explosions happening and so on and so forth. Only way to overcome that is to increase our UA by V. If I increase from 15 to 20 to 25 to 30, everything delta H is the same. You see, if I increase UA by V, how the peak is reducing from 0.8 to 0.6, 0.65 to 0.2, 0.3 to just 0.1. See how peak is reducing, how I am becoming safer and safer. So increase UA by V, increase surface area to per unit volume, break the reactor into smaller sized reactor. So surface area per unit volume will be more. Instead of taking one 20 meter cube reactor, We might take two 10 meter cube reactors. Surface area per unit volume would be more. Instead of having a jacket, put coils inside the reactor. Increase surface area for heat removal. Right? So this was a short lecture, but I wanted to tell you that all these things you have to analyze. Some homework for you is, if you are referring to Fogler's book, 4th edition, we are on chapter 9. Solve problem number P9-5, 9-7 and 9-17. If you are looking at 5th edition, we are on chapters 12 and 13. So it's a small lecture, but it tells you that how you have to worry about how the temperature rises, how fast it rises, and what kind of implications are there in terms of safety of the reactor. So batch reactor, you would have thought, so easy. Put the reactants, put the catalyst, allow it to react, and after 5 hours, 6 hours, whatever it is, we will remove. But within that 5-6 hours, if it's an exothermic reaction and if it is heat transfer area is not available, you could have a very large peak, and at that peak you can have other side reactions which you had not thought of happening, and then it will lead to runaway condition. You will lead to explosions. So batch reactors, you have to be very careful and analyze them from how the temperature versus time profile will look like. Now do you understand why this part of the course is called as real life reactors? We have not done anything else. We have only talked about batch reactors, well mixed continuous reactors and plug flow reactors. But within these three, you see how exothermicity and how real life heat removal considerations come into picture that influences our reactor design. Your design has to account for all of these things. Only when all of these are accounted, then you have a proper design. Otherwise, you will design something, it will explode. It is of no use to anybody. It is a liability. Be very careful. That's why reactor design has to be done very carefully, but it's a very interesting and a very rewarding and very challenging field as well. All these different aspects have to be considered: fluid flow, heat transfer, mixing, thermodynamics, whatever it is there. Maybe something vaporizes, pressure builds up, gas liquid equilibrium, something vaporizes, some equilibrium is reached between gas and liquid. All those things have to be considered. All the subjects knowledge you will require when you start designing reactors. So we have to be very careful, analyze from all angles, and then you have a design. Not just, whereas undergraduate course, what are you thinking? You thought that residence time we calculate, reactor design is complete. Is it? No, it's not. All these things you have to account for, which you did not in your undergraduate course. That's why it is an advanced reaction engineering course. All these considerations are required. Henceforth, when you design a reactor, take into account all these considerations. So this lecture ends here. This part of the syllabus ends here. Next part of the syllabus, we'll start looking at non-ideal flow, okay, residence time distribution, those kinds of things.